failure in New York brings about deadly consequences. Dozens die in a grain elevator explosion caused by dust. The roof of a sports arena falls 60 feet to the ground, sending 5 construction workers to their deaths. A runaway freighter smashes into a wharf, endangering thousands of lives. Britain's dream of lighter-than-air travel ends in tragedy. Now, engineering disasters on Modern Marvels. On the morning of April 5th, 1987, a light shower fell on the already rain-soaked I-90 Thruway Bridge, crossing over Schoharie Creek in upstate New York. It was the final vestige of a torrential downpour that caused the Schoharie Creek to reach a near-record flood level. As traffic crossed the overpass, without warning, a 200-foot span of the bridge collapsed. 2 vehicles immediately plummeted 80 feet into the raging creek below. Before the bridge could be closed to traffic, 3 more cars fell through the void. There were no survivors. The tragic collapse of the Schoharie Creek Bridge led to an immediate investigation to determine the cause of the failure. The 540-foot-long bridge over Schoharie Creek was part of the New York State Thruway, a superhighway connecting New York City to Albany and then west to Buffalo. Construction of the original bridge began in 1953, featuring a design that was standard for its time.
It had 2 abutments, 4 piers, and 5 spans. The span lengths on both ends coming off the abutments were 100-foot spans. Spans 2 and 4 were 110-foot spans, and span 3 was a 120-foot span.
The 4 piers that supported the superstructure consisted of 2 columns connected to a subbase, or plinth, resting on spread footing. To protect the bridge against the potential erosion of the riverbed, the contractor attempted to use steel piles to anchor the footings.
When time came for the contractor to drive those piles, he found out that the material was glacial till, which is a very compact material of stones, rocks, and earth that was compacted by hundreds of, if not thousands of feet of glaciation on top.
There was a number of boulders of different sizes, making it very difficult to drive piling into the bottom of the river. The designers finally concluded that the glacial till at this site was sturdy enough to support the foundation system of the substructures.
The 1951 flood of the Schoharie Creek also played a role in the decision. It was the largest flood on record and was the result of a severe storm that struck upstate New York. The resulting precipitation produced a peak flow of 37,900 cubic feet per second. But because that flood was believed to be a rare occurrence, the bearing capacity of glacial till was felt to be sufficient. Therefore, piles were considered unnecessary and riprap was used instead.
Riprap is large angular rock that is placed around the foundation to protect the footing and the substructure from water flow.
This is not foolproof. In other words, it works some of the time and it needs continuous checking and investigating that the riprap stays in the original position.
But this crucial element of safety was hindered by the bridge's ambiguous design plans, which did not specify exactly how the rock should be placed.
If you looked at the south elevation, it showed riprap going down around the footing. They also showed steel sheeting in around the foundation that eventually would be filled with riprap. If you take a look at the cross-section at the center line of the bridge, it just showed a covering of riprap over the glacial till, which made it somewhat difficult for the contractor to decide which way it was really supposed to be built.
Investigators concluded that riprap was placed only around the surface of the piers. The Schoharie Creek Bridge opened to traffic in October of 1954. Almost 1 year later, the integrity of the structure would be severely tested. In August of 1955, Hurricane Diane dropped 9 inches of rain along the northeastern United States, increasing the volume of the Schoharie Creek to more than twice the flow brought by the 1951 flood. From the surface, the bridge appeared intact, but the high flow had attacked the riprap located on the upstream side of the piers. pushing the rocks downstream and making the footings vulnerable to scour.
Scour is the creation of a hole, usually at the face of a pier or an abutment. What happens is that the water hits the face of a pier. It usually goes down and then up again. And what it does, it takes the earth, then cobbles and stones, and creates a hole right in the face of the pier or an abutment.
Well, scour is kind of an interesting animal because of the fact that once scour occurs, when you have these high floodwaters, as the flood recedes, these scour holes can actually refill up with material. So it makes them somewhat hard to detect.
After the record flood of 1955, 4 additional floods also exceeded the velocity of the 1951 flood. Yet the riprap at the Schoharie Creek Bridge was never replaced, and an underwater inspection of the bridge was never performed. In April of 1987, a major storm struck upstate New York, setting the stage for a disaster.
The storm in 1987 was one of the biggest storms on record, and it created a huge amount of flow. It was something like 12 foot high. It was going about 10 miles an hour, and it was carrying all kinds of debris.
At 8:45 a.m., the Burtonsville gauge, located 13 miles upstream of the bridge, recorded a peak flow of 64,900 cubic feet per second, the second highest on record. 2 hours later, the turbulent flow reached the Schoharie Creek Bridge. A bend in the channel brought the fastest moving section of the flooded creek to the glacial till on the upstream side of Pier 3, now unprotected by riprap.
The soil pressure at the very back end of the scour hole increased significantly, changing the stress flow throughout the plinth because you don't have the support at the front end. And as that scour hole changed, it changed the stress configuration in the foundation and finally caused the plinth to fracture.
The plinth fracture at Pier 3 dropped the column 4 feet into a scour hole. The resulting loss of stability to the superstructure brought 2 spans of the roadbed crashing down into the raging creek. The debris from the collapse diverted the flow to Pier 2, which failed 90 minutes later, also due to scour.
The reason that the scour hole occurred was that we did not have adequate riprap protection around the scour hole. This substructure counted on the placement of riprap to provide protection for the foundation. That had to be checked routinely throughout the life of the bridge.
The failure of the Schoharie Creek Bridge brought national attention to the vulnerability of America's bridges to scour. It spurred new legislation, demanding the underwater inspection of bridges on a biannual basis.
The impact of the failure of this bridge has been far and wide throughout the United States and the world. It forced us to go to the U.S. Geological Survey and fund a scour study that lasted about 10 years.
Soon after the collapse, the Schoharie Creek Bridge was rebuilt with the intent of making it one of the safest bridges in the country.
It cost probably 2.5 times what a normal bridge would have cost. They drove huge piles, the biggest piles there is, to rock 40 or 50 foot deep. And this bridge should not collapse again. It is probably the best built bridge in New York State.
On a warm summer day in upstate New York, a team from the U.S. Geological Survey has returned to the bridge that was the impetus for their extensive research into scour.
Inside here is an acoustic Doppler current profiler. This device can be used to detect scour holes. It can be used to measure velocity from real close to the bottom to all the way up to the surface. So we actually get an idea of how fast the water is moving as well as how deep the holes and stuff are.
We're going to measure the stream bottom closely around Pier 3 on the far bank over here because that was the location where the previous pier had collapsed in 1987. That side of the stream is prone to scour as a result of the swift velocity from the stream.
True to the history of the Schoharie Creek, the acoustic Doppler profiler detects a 5-foot scour hole next to Pier 3. Fortunately, the hole had already been covered with riprap to protect against further erosion.
There are many other USGS districts that are collecting scour data in addition to New York. All these data are being entered into a national database which researchers can continue to analyze to understand the process of scour better.
The failure of the Schoharie Creek Bridge has contributed to the overall safety of bridges across America. But this added safety came at the cost of 10 lives, who in death have helped protect millions. Engineering disasters will return on Modern Marvels. Along the west bank of the Mississippi River lies the city of Westwego, Louisiana. On December 22, 1977, the eyes of the nation were fixed on this small southern city when a 250-foot grain elevator exploded.
It was heard by people over 10 miles away from the facility. The energy released in this explosion was equivalent to many hundreds, if not thousands of pounds of TNT.
There was fire and smoke coming from the tops of the silos. There was debris everywhere. It was total devastation.
Perhaps the only thing more shocking than the magnitude of the explosion was the cause: grain dust.
Any material that can burn will burn rapidly and explosively if it's small enough. Grain produces dust when it's handled. That dust burns so rapidly, it's explosive.
The disaster in Westwego was not the first dust explosion at a grain elevator facility, but its severity was unmatched, and it would serve as a wake-up call for the entire industry. Because of their design, grain elevators are highly susceptible to dust explosions. The actual elevator at a grain elevator facility typically consists of a multitude of buckets connected to a vertical conveyor belt. When a barge is unloaded, the bucket elevator scoops up grain and carries it to the head house. From there, it is sorted by grain type and dropped into concrete silos.
Grain elevators are designed to move tremendous quantities of grain. When you handle these materials, the generation of dust is inevitable. If you look at the 4 factors required for a dust explosion, the presence of dust is ever present. We have enclosure or confinement of the structure itself and oxygen in the air. Therefore, all that's needed is a spark or ignition source to have a dust explosion.
In the United States, 60% of the grain that is exported is carried along the Mississippi River, making Westwego a natural location for a grain elevator. And in 1977, the Westwego facility was a major employer to the city.
When Mark got the job, you know, he was happy with it because it was so close to home. I never thought it was a dangerous place to work.
Before Mark LaBiche left for work, he alluded to a potential danger at the facility.
They were supposed to close the grain elevator down for cleaning, and I know because Mark had told me this.
On the morning of December 22nd, Mark LaBiche was working in the grain elevator's head house. An unusual cold front was passing through Westwego, dropping the humidity to a very low level. With static electricity and grain dust in the air, the elements needed for an explosion came together.
About 9:15, I heard an explosion, and my daughter and I went up to the river road. All we could see was a lot of dust and a lot of concrete all over the place.
There were people walking around covered in grain dust. Many of them were digging through debris trying to find co-workers and things like that. Helicopters were there probably within 30 to 40 minutes after the blast, and they were trying to rescue people off the tops of the silos.
The radio said it was the riverside of the grain elevator, and I said, thank God, because Mark's working in the head house. But when we got there, it was the head house that blew.
Approximately 100 feet of the head house was destroyed. Fractured concrete rained down on the grain facility's control room, killing dozens. Among them was Mark LaBiche. The shockwave from the first explosion traveled through the facility, causing additional grain dust to become airborne and to combust. A number of secondary explosions ignited instantaneously, completely destroying the facility.
The explosion in Westwego involved a very large quantity of dust built up in a very large structure. Due to the magnitude of this explosion, the exact cause cannot be pinpointed but is likely a malfunctioning mechanical component on the bucket elevator, such as a failed bearing, or on a ventilation fan in the head house.
The resulting mechanical friction would have produced a fatal spark or enough heat to cause the dust to ignite. 36 people died in the accident. It remains the deadliest grain dust explosion on record. In the years that followed the Westwego disaster, the grain elevator industry has taken extensive measures to minimize the potential for grain dust explosions. Today, roughly 20 miles outside of Westwego, in Destrehan, Louisiana, the Bungie grain elevator utilizes a variety of safety methods found throughout the industry.
The incidents of 1977 in the grain industry was kind of a wake-up call, if you will, for the whole industry to realize that we had to give a renewed focus and much more emphasis on root cause analysis of what causes these type of explosions.
One of the critical safety measures implemented by the industry is to closely monitor potential ignition points. Primarily, the bucket elevator, which is the cause of 40% of all grain dust explosions. If a bearing overheats, or the conveyor belt is misaligned, heat sensors located throughout the elevator legs will notify personnel of a potential explosion.
We have over 700 of these discrete points that we're actually monitoring the temperature all the time. And that information is conveyed back to the control room that is sensing these temperatures, giving us alarm if it gets to a certain level, and can even shut down the equipment automatically if it gets to a higher level.
However, if there is an accidental explosion, measures have been taken to contain the blast wave, thus preventing the often deadlier secondary explosions.
5, 4, 3, 2, 1.
How it works is that the suppression device actually senses the increase in pressure caused by the early stages of an explosion and would dump a chemical into that bucket elevator casing that would immediately suppress and eliminate the explosion.
The chemical agent is dispersed within 80 milliseconds, stopping the explosion in its tracks. Making sure that dust doesn't accumulate around the facility is also vital to minimizing secondary explosions. And as a direct result of the incident in Westwego, grain elevator head houses are no longer located above employee offices.
Spreading the facilities out, moving the control rooms to remote locations, all of those came at a cost, efficiency, but was worth it from the safety payback.
It's a real success story. We went from a time in a peak year over 60 people were killed in agricultural dust explosions in the late 70s, and a great reduction in risk has been achieved through the engineering evaluation of these types of accidents and taking appropriate steps based on the knowledge learned.
And the numbers proving. From 1976 to 1985, there were 143 deaths as a result of grain dust explosions. From 1986 to 2003, that number dropped to 33. 5 days after the grain elevator explosion in Westwego, Louisiana, a grain elevator in Galveston, Texas also exploded, taking the lives of 18 people. Engineering disasters will return on Modern Marvels. They are modern-day versions of the Roman Colliseum, built to entertain tens of thousands of people. But if engineering mistakes are made, they can collapse without a moment's notice. And in the late 1970s, arena collapses became eerily common. In 1978, the Hartford Civic Center suffered a structural failure just hours after hosting a sporting event. In 1979, the Kemper Sports Arena also came crashing down. Both arenas had a common point of failure: the roof.
What normally causes roof failures really has two origins. When structures that have been completed fail, they fail either because they're overloaded or because there's some problem of deterioration perhaps, or some other issue where the structure's performance under load is different than the assumptions. The roofs that never make it out of construction, that never are completed, those roofs collapse during construction, and one of the most prevalent causes are some form of instability.
Such was the case in 1979, with the Rosemont horizon. In 1978, the village of Rosemont, Illinois, a Chicago suburb, broke ground on an ambitious 18,000-seat capacity sports complex.
When we had the initial press conference and announced that we were going to build an arena, they said, "Now wait a minute, Mayor, how many people live in Rosemont?" And I said, 4,000. "And you're going to build a convention center, an arena to seat how many?" I said, "About 18,000. He said, "Well, how are you going to fill the arena?" I said, "Well, you know, really, the arena is going to serve more than just Rosemont. We're in a metropolitan area here that has got 8 million people living in it. So if you have a ticket, even if you're not in Rosemont, we'll let you in."
The decision to build the arena was largely influenced by Rosemont's close proximity to Chicago's O'Hare Airport, one of the busiest in the world. But the airport was responsible for a great deal of noise pollution, enough to demand a unique type of roof for the arena.
Wood was used for a dampening effect from the aircraft noise. It is practically dead center of one of the glide paths coming in on the runways. So the wood was used for sound insulation.
The only thing that was better would have been cork. And of course, cork, you can't make cork stand up there.
The design for the roof of the Rosemont horizon called for 16 glue-laminated arches, each spanning 288 feet.
If you can keep the arch in a single plane, like a piece of paper, it is a very efficient structural system, one that's very strong for its weight. The thing that's important to recognize, though, is you must make efforts to keep it in plane. As soon as the arch begins to move out of plane, in other words, to twist or to rotate, it immediately begins to lose strength. It creates conditions which allows the arch to behave badly, and ultimately it will collapse.
Each arch of the roof was fashioned from 3 distinct pieces. 2 end trusses were connected to 2 concrete buttresses, and then the crown truss was placed in the middle. The 2 end pieces were then spliced to the centerpiece by prefabricated metal sheeting. Running perpendicular between the arches was a series of wood beams, known as purlins.
And those purlins serve 2 functions. They support the roof decking and the roof materials, but more importantly, they laterally support the arch, which is a very slender element. The arches are absolutely critically supported by the purlins.
As the arches were being assembled, problems quickly arose. The arch sections didn't line up with the splice holes. Also, the spacing between the arches was off by as much as 12 inches in one span, making the purlins difficult to place. Because of the misalignment, some of the connection holes were enlarged, and many of the bolts were omitted. Temporary bolts called drift pins were used instead.
One of the principal differences between a wood structure and a steel structure relates to the connections and the bolting processes. The erectors in the Chicago area would rely on steel erectors, people that are familiar with such structures as the Sears Tower, John Hancock, and other notable steel structures. In those structures, it's common to not employ all the bolts, to put all the bolts in the connection, because of the difficulty in fitting up a multi-bolted connection. In wood, we have to be careful that all of those bolts may be necessary for our delicate friend, the arch, who has a tendency to get out of plane.
In the early morning hours of August 13th, 1979, the final arch of the roof was being erected when a 20-mile-per-hour gust of wind blowing perpendicular to the arches led to disaster.
The arches became unstable and collapsed, moving toward the west, and it formed somewhat of a progressive type collapse in which one arch failed, released the lateral bracing to the next arch, loaded it laterally, it failed, then the next, then the next, then the next.
The timber roof fell 60 feet, splintering on the ground as if it were a pile of matchsticks. 5 construction workers were killed in the accident. The arena was completely destroyed. An investigation into the failure of the Rosemont horizon found that 54% of the 966 required bolts were missing from the roof. Of the 444 bolts that were in place, 338 had no nuts.
The principal reasons for the collapse of the roof relate to the absence of lateral bracing on the main arch members. That lateral bracing is accomplished by fully effective connections between the purlins and the brace to make sure that the arch can't move laterally.
In the days that followed, the decision was made to rebuild the Rosemont Horizon following exactly the same design plans, but with a different contractor.
When we erected the roof the second time, each 24-foot section was completely installed and 100% complete before we moved on to the next section, which in essence allowed each one to be 100% secure before we moved the supporting structures.
The Rosemont Horizon has been renamed the All-State Arena and has served its community for more than 20 years. Because the new contractor followed the same design plans, the roof failure of the arena demonstrates that a structure's stability relies as much on the diligence of the builder as it does on the skill of the architect. Engineering disasters will return on Modern Marvels. On December 14th, 1996, a fully loaded freighter lost power while traversing the lower Mississippi River. Unable to navigate, the runaway ship headed straight for two moored vessels packed with nearly 900 passengers and a marketplace filled with thousands.
There was no doubt in my mind that one time we were going to kill hundreds of people.
Less than a mile from the French Quarter lies New Orleans' second biggest attraction, the Riverwalk Marketplace. Built along the banks of the lower Mississippi River, the Riverwalk shares the property with a Hilton Hotel. Both locations enjoy spectacular panoramic views of the river, but that view comes with a risk.
The lower Mississippi is a place that can be compared to a freeway in New York. It's very busy. 6,000 ocean-going ships a year.
There's a lot of twists and turns. You have deep places, you have shallow places. It's the hydraulics, it's the physics, the eddies, the currents. All those combination of things mixed together that make this probably the most hazardous port in the United States.
Because of the danger of transiting the lower Mississippi, river pilots escort vessels into port. When pilot Ted Davison boarded the Bright Field, he was given no reason to believe the ship was in trouble.
I went through a lengthy discussion with the captain whether or not the ship was ready to go and if it was seaworthy, and he answered everything in the affirmative. And at that point in time, we got underway and came down the river.
What the captain didn't tell Davison was that the Bright Field had endured a series of engine malfunctions along its journey from Indonesia to New Orleans.
The story of Brightfield started long before Brightfield arrived to Mississippi River. The ship has suffered numerous failures of the engine system. The ship was a problem to the extent that when it arrived to the U.S. coast with its cargo, the owners fired the engine master for lack of maintenance and proper handling of the mechanical system of the ship.
At approximately 2 p.m., as the Bright Field passed under the Crescent City connection bridges, the ship turned left, pointing toward the Riverwalk Marketplace and two commercial vessels moored alongside the wharf. Instantly, the pilot knew something was wrong.
Everything went quiet, and no longer did we have any vibration. Upon that, I immediately looked at the ship's tachometer, and it had gone from 60 to 70 revs to zip. And I knew right away we had a serious engine problem.
The Bright Field's main engine had shut itself off due to low main engine lubricating oil pressure. Investigators believed the malfunction resulted from contaminants in the oil, clogging the pump's filter. Or low levels in the sump may have caused air to be pumped into the system, bringing about a rapid depressurization. 3 targets lay in front of the runaway freighter, a cruise ship with nearly 300 passengers, and a gaming vessel with over 600 passengers. In between them was the Riverwalk Mall, crowded with over 7,000 patrons.
The actions I took was to call the Coast Guard, to start blowing the danger signal, to get on the radio and ask for tug assistance. And I repeatedly told the captain to let go both anchors.
But the blaring of the ship's horn made it difficult for the crew to hear Davison's command to drop anchor.
The communication was happening over radio. The radio was not audible to the person who was supposed to receive the signal. I'm talking about the person who was supposed to be responsible for anchor.
There was no doubt in my mind we were going to strike and slice through a passenger ship with people on it. And instead of this ship continuing to turn to the left toward the passenger ship, at the last moment, it went right.
Still with no way to slow down, the Brightfield headed straight for the unsuspecting patrons at the Riverwalk Marketplace. At a speed of 14 knots, the Brightfield smashed into the wharf, shattering concrete as if the ship were an icebreaker.
When Brightfield came to shore, it came in contact with a walkway that is along the shopping mall and which is in front of a hotel. Bow of the ship went into the walkway, crushed it basically, and kept moving into the shopping mall.
Actually, I felt very little on the bridge of the ship. What amazed me, though, is to see the buildings crumbling like they were made out of paper mache. I was asking myself, is this made out of concrete or paper?
When the ship finally stopped, it was perfectly berthed between the two moored vessels. Moments later, the Coast Guard arrived to secure the scene. Rumors spread about loss of life.
When I first came to the property, Mayor Morial told me 3 confirmed dead, another 3 probable. We don't know how many people are going to be in there. This could really be bad.
Fortunately, because of the time of day, no guests were in their rooms at the Hilton. Miraculously, there were no fatalities from the accident. But 4 people were severely injured. And property damage was in excess of $12 million. Today, the fortunate outcome of the Brightfield incident has not been lost on the Riverwalk property owners or the U.S. Coast Guard.
When the Brightfield occurred, we had no warning. Our security captain had just received a call saying a ship is headed to the shopping center, you need to evacuate. He stood up and the ship hit. I mean, there was a certain amount of luck, divine providence, however you feel about that sort of thing. We then put in, with the introduction of the port and the Coast Guard, a riverfront alert system was installed.
The River Alert Network is an advanced warning system. Upon receipt of a vessel which is experiencing some sort of a problem, they would notify either our vessel traffic service or our Governor Nichols light operator. Once we receive knowledge of that, we would activate a system by pushing a button. Once we push that button, we also follow up with a voice notification to the property tenants located along the riverfront, notifying them that there is an issue which they need to be aware of.
To complement the Riverfront Alert Network, the Riverwalk chose to invest in an additional security system that monitors vessel activity along the Mississippi River.
We have 4 cameras that face out to the river. If she determined that there was a danger, then what she would do, she would pull the maritime alarm, and then that would tell people to evacuate the property away from the river. If we would have had this system in 1996, the operator would have focused on the ship, seen that it had lost power, and would have ordered an evacuation. We'd have had a full 3 minutes, which would have given us time to get people safely out of the property.
Although these new safety systems will help expedite an evacuation, they won't stop another Brightfield incident from occurring. It's simply one of the inherent risks of placing a highly populated commercial center along one of the most dangerous bends of the Mississippi River. Engineering disasters will return on Modern Marvels.
The back motors of the ship are just...
It's perhaps the most famous disaster ever recorded.
It burst into flames. Get it started, It's rising, it's rising, terrible. Oh my, get out of the way, please. It's bursting into flames.
When the Hindenburg fell to earth in a ball of fire in 1937, the world had a front row seat.
Oh, all the humanity and all the passengers screaming around it.
But in 1930, no cameras were present to capture the disaster that befell the R-101 airship, which burst into flames in an equally spectacular fashion, killing 48 passengers and ending the British airship program. During the early 1900s, the majestic lighter-than-air dirigibles ruled the skies over Europe. While the airplane of the 1920s remained a work in progress, the airship was viewed as a sophisticated and efficient mode of air travel.
Airplanes were rickety and unreliable and noisy and uncomfortable and drafty and didn't carry many people. The Zeppelins had established an excellent reputation for reliability and safety, and they were so much more comfortable and would carry so many more people.
After World War I, the British Empire controlled roughly 1/4 of the Earth's surface. Looking for a way to connect its far-flung empire, Britain developed a program to build 2 airships. The R-100 would be built by private enterprise and would connect Britain to North America. The R-101 would be built under government control and would bring Britain closer to India and the Far East.
The R-101 was designed to be the largest airship that had ever been built. It was designed to have range sufficient that with just a couple of intermediate stops, it could go from England to India in less than a week, carrying 60 passengers in remarkable luxury.
Although Germany had a successful airship design with the Graf Zeppelin, Britain sought to improve upon it with the R-101.
The structural design and layout of the R-101 was very innovative. The dirigible itself was built in circular frames that had individual structural rigidity. Well, to build these rigid frames and still have this thing fly, the frames had to be built out of a very new material for the day called aluminum.
In a typical dirigible, passengers and crew were carried in gondolas that were suspended below the gas bag. In the R-101, they decided to streamline the vessel, and the passengers were actually inside. There were 2 levels, like on a ship, 2 decks, with all manners of staterooms and dining rooms and recreation rooms, smoking lounges. It was very luxurious.
Non-flammable helium, which was used on the U.S. airship Shenandoah, was not readily available in Britain. Thus, hydrogen, which is highly flammable but provides more lift than helium, was chosen for the R-101. 16 gas bags were held in a mesh screen containment above the passenger accommodations. Each bag weighed approximately 1,000 pounds. Together, they were designed to give the R-101 a gross lift of around 150 tons, more than any other airship ever built. In October of 1929, the 732-foot R-101 was taken out of its shed in Cardington to undergo preliminary testing in preparation for its maiden flight to India. Immediately it became apparent that the lighter-than-air ship wasn't all that light.
When the R-101 was first tested, they discovered the hard way that they had overbuilt it, and it was much heavier than they'd planned. It didn't have near the spare lift that they wanted or needed for the mission.
They discovered that the gas bags themselves, which, believe it or not, are made out of cow intestines, which are stitched together and then coated with varnish. These gas bags are leaking prodigiously. In fact, it has been reported that they were losing about 22,000 cubic feet of hydrogen per day from pinhole leaks.
An even more alarming problem arose in June of 1930. While the R-101 was moored to its tower, the outer covering along the starboard side suffered a tear that extended 140 feet. A fissure that would have been fatal had the ship been in flight. Engineers believed that gas bag leakage could be controlled with ballast, but to give the R-101 the required lift needed to journey to India, they opted for a radical solution. They cut the ship in half, adding an extra bay and an additional gas bag, making the world's longest airship even longer.
It was nearly 800 feet long. When you have something that's that long, the pressures on one end of the ship can be very different from the other end of the ship. You can have wind shears that act on the nose that don't act on the tail. So there's going to be some flexing and twisting, either nose to tail, up and down, or from side to side.
And the metal structure was designed to actually flex, but that created some problems later on in that the fabric outer covering didn't flex in the same way that the rigid metal structure did.
By 1930, the R-101 was massively over budget and far past its original completion date. Political pressure over the ship's maiden flight to India began to mount.
The decision to take the R-101 to India was singularly driven by one man, and that was the first Air Lord, Lord Thompson. And he was the principal advocate and the guy whose prestige was on the line for the success of this program. And he fell back into his mode of management, which had served him well all in his career. Insist action occur, damn the doubters, we're going to go.
This was a government project, government funded, government controlled. When the Air Minister said, let's go, they went.
With great anticipation, 54 people, including Britain's Air Lord, boarded the R-101 on October 4th, 1930.
When the R-101 takes off from its hangar in Cardington, it symbolizes embarking upon the longest airship voyage in history. The first Air Lord is going to go all the way to India and back and do it in 2 weeks, which at the time would have been on the order of Lindbergh's flight across the Atlantic.
After the R-101 took off from Cardington, it circled over London, giving onlookers a chance to gaze at Britain's newest technological marvel. It then headed for the English Channel on its way to France. It would be the last time Britain would see the R-101.
They took off on a rainy, misty day, and the winds were along the path of travel in the 30, 35 mile an hour range. Not the most favorable conditions for dirigible travel, but certainly not the sort of things you would expect to wipe out this particular craft.
But just after 2 a.m., as the R-101 was passing through a rainstorm, the ship began losing altitude.
The captain assumed that the fabric had become waterlogged and too heavy. What he didn't know was that the top fabric from the nose back had ripped off, and the gas bags were exposed to the storm, to the rain, to the wind. And while it was only a moderate wind, 25 miles an hour, the airship was going at about 50 miles an hour. So this was hurricane-force winds blowing on these gas bags.
The high winds violently shook the gas bags closest to the ship's bow, causing them to chafe against the airship's frame. The added stresses turned the numerous pinhole leaks into a fatal fissure, accelerating the loss of hydrogen and causing the dirigible to nose over. Realizing that a crash was inevitable, the helmsman cut the ship's engines to soften the landing.
It's estimated they hit the ground at less than 13 miles an hour. Not even a bad bicycle fall, if the truth be known.
However, a spark from the twisted metal ignited the gas bag closest to the bow of the ship, setting off a chain reaction of fast-moving fires that spread from the bow to the stern, engulfing the airship in flames. Of the 54 people on board, all but 6 died, including Lord Thompson. Several of the survivors testified that the front end of the airship's outer covering had ripped off, a crucial piece of evidence that may have explained the loss of altitude. Covered by the dark cloud of the R-101's failure, the sister ship R-100 was dismantled and sold for scrap. The skeletal frame of the R-101, which represented the best technology in British lighter-than-air travel, was eventually sold for scrap as well, putting an end to the British airship program.